let me... Okay, this is the Game Changer seminar series of the International Space Science Institute. I'm Mark Sargent, EC's Science Program Manager, and I'll be your host for today. Welcome everyone, and it's a slightly early start compared to other weeks, but we're looking forward to Raphaël's talk, which is the last in our current series on habitability from galactic to microbial scales. And to finish off, Rafa will take us to galactic scales. So yeah, just a few words about Rafa. I met Rafa several years ago when we were office mates at CEA Saclay in a baking hot room in summer right underneath the roof. And before that, he had done his PhD jointly in Munich at ESO and the LMU. And after his time at CEA Saclay, his first postdoc, he then moved on to the Korean Institute of Advanced Studies in Seoul, where he did another postdoc before he then moved to Chile. And his current position in 2018, so he is currently a tenured assistant professor at the Catholic University of Valparaiso. And yeah, Rafa is a man of many interests, has done a lot of work with respect to galaxy formation and evolution, especially also focusing on galaxies in clusters. And this work has led him to develop some of the tools which he has used to estimate the habitability question in a galaxy evolution context. So Rafa, we're very much looking forward to your talk. We'll organize this as usual, as we have done for previous seminars. So if you have a question, feel free to put it in the chat while Rafa is speaking, or raise your hand. I'll keep track of the order. And then once Rafa has concluded with his presentation, we will alternate between raised hands and questions in the chats. And for raised hands, Lily then in the background, as usual, will unmute you and you can ask your question. But yeah, to begin with, here's Rafa with his presentation on the habitability of galaxies and the spread of life. So Rafa, the stage is yours.
Thank you. Thank you, Mark. And again, thank you for agreeing to move this seminar forward by an hour. Sorry, everyone. That is to accommodate my schedule. So as he said, I am primarily an extragalactic astronomer, and I deal mostly with distant galaxies, very distant galaxy clusters, from both an observational and a theoretical point of view. And this is where this curious intersection that I am going to present came about. But first, let's go back a little bit in time and talk about the idea of the plurality of worlds. So the idea of the plurality of worlds in which the universe is filled with a vast number of planets that are similar to our own, can be argued to have roots in antiquity, but it really took off after the Copernican revolution and the decentering of the Earth in the cosmos. And naturally, it very quickly made the jump from philosophy to literature, speculative fiction, sometimes playing some fears of contamination, like in H.G. Wells's War of the Worlds. In the 20th century, it has become a staple of popular culture and is now entirely integrated into our thinking, to the point that we don't really question it. But from a scientific point of view, the exploration of the solar system by robotic probes in the 20th century really hammered home how unforgiving and hostile the universe could be to life as we know it. It's less Star Trek and a little more Mad Max. So the question of our uniqueness has therefore stayed relevant. And an early mid-20th century attempt at formulating this question is the so-called Drake equation. The Drake equation is just a product that relates the numbers of possible others to a series of factors such as the formation rate of stars in our galaxies, the fraction of stars with planets, and the number of habitable planets per star, etc. Most of these parameters were and still are entirely unknown. So, for example, the rate of star formation could be inferred at the time of formulation. The fraction of stars with planets can actually now be estimated from observation, which is a fact I still find wonderful. And the number of habitable, or the fraction of habitable planets can be derived from the second parameter, tentatively. But for all the others, we don't have any data, and you might as well flip a coin. Just pick a value you like, and you won't be, you will be as close or as far to the truth as anyone else. Now, finding the value of that second parameter, that is the fraction of stars with planets, has only become possible relatively recently in the last quarter century, thanks to prodigious advances. We now have dedicated telescopes and instruments, both in space and on the ground, to detect and characterize exoplanets. And in reality, anyone with a small telescope and a good astronomical camera could actually get in on the action. Naturally, discoveries are not guaranteed. The third parameter, which is the fraction of habitable planets per star, is related to the second, which is the number of terrestrial planets per star system, through a concept that is called the circumstellar habitable zone, which you certainly heard about. In essence, it just defines a shell, a range of orbits around a given star, where liquid water, which is considered absolutely essential to life, can exist at the surface of planets that are not too dissimilar to the Earth. Anything outside of it will be either boiled away or completely frozen. And the Earth, obviously, is in the habitable zone of the Sun. However, being in the habitable zone does not ensure that the planet will be inhabited or even inhabitable, because that will depend on its mass, its atmospheric composition, its atmospheric pressure, and even its surface composition. Based on these factors, the outcomes can be very different. By analogy, people have also started to try to define a galactic habitable zone. That is, in a spiral galaxy like ours, of which this is a representation, this would be the region where terrestrial planets or Earth-like planets can form and thrive within the habitable zone of their stars without being disrupted by stellar evolution, blasted by supernova explosions, or scorched by the radiation emitted by matter falling into the central supermassive black hole. And in this context, it's sometimes thought that the outer edge of the galactic disk should be unsuitable because of a lack of heavy elements, implying that rocky planets would essentially be rare. Now, to non-astronomers, if there are any in the audience, we use and I'm going to use the word metallicity to describe the fraction of elements heavier than hydrogen or helium. So lithium is a metal, oxygen is a metal, carbon, nitrogen, rare gases, everything is a metal, but hydrogen and helium. Now, more recently, we have also extended this concept of habitability to other galaxies using, at first, simple arguments based on metallicity. And these would, in principle, suggest simple correlations between the frequency of terrestrial planets and the mass and star formation of galaxies, as well as with cosmic stars. But those are pretty bare bones, which is why we wanted to make a better model, a model with better resolution, let's say, using the expertise that we had in modeling stellar populations in galaxies. And the implicit question we want to answer here, naturally, is, are we living in a nice neighborhood? What are the property values? Should we worry and install an alarm, or that kind of thing? So let's make a stellar population model, but with planetary habitability baked in. What would be the ingredients? Well, small scales, obviously, we need the circumstellar habitable zone. And here we use the formulation of Gobat from 2013, in which the inner edge of the habitable zone is just shy of a runaway greenhouse effect. And the outer edge is defined by the point where you cannot add any more CO2 to the atmosphere unless you start just shielding from sunlight. But roughly the radius and position of the habitable zone will depend on the square root of the luminosity of the star, therefore more or less on the square of its mass, which means that smaller stars will have much tighter habitable zones. The second ingredient comes from planetary distribution functions, exoplanet statistics, which we now have, especially in the last 10 years. And before that, we arbitrarily consider that habitable planets are only found around suitably mature stars in their main sequence phase. That is, in the phase where they fuse hydrogen into helium. And mature because the Earth, in the first billion years, was probably habitable marginally, but didn't really much resemble what we think of today. Now, the fraction of terrestrial planets, rocky planets around stars, apparently seems to be somewhat insensitive to metallicity, at least above a certain threshold. So we assume a flat distribution with metallicity, adding a slight anti-correlation with metallicity to mirror the increasing fraction of hot Jupiters. This would be the plot on the left, on the bottom left. Hot Jupiters are gas giant planets, which usually form in the outer parts of a solar system, but that orbit very close to their host star. And they constitute spectacular evidence for the phenomenon of planetary migration, which is thought to happen, which happens relatively early on when a planetary system is still forming within a circumstellar disk. Now, since those are really massive objects, when passing through the inner system, they would severely disrupt the orbit of any rocky planet forming or already formed there. And therefore, we assume that the presence of a hot Jupiter is incompatible with the presence of an Earth-like planet in the habitable zone. Now, let's move to larger scales, galactic scales. Now, at galactic scales, we need to consider the distribution of stars within a galaxy as a function of several characteristic parameters, in particular mass. That is because stars do not actually form isolated, they form in bunches and in groups, in clusters. When that happens, typically only very few, very massive blue hot stars are formed, slightly less massive stars, even more intermediate mass stars like the sun, and even more red dwarf stars. As a function of stellar mass, this actually follows a power law, more or less a simple power law function, which we call the initial mass function. However, this is in a star-forming region. Massive stars don't live as long as red dwarfs, for example. So in regions of the galaxy that are slightly older, that distribution function is going to become truncated. And there is an additional complication because we can assume that the initial mass function is constant over an entire galaxy for convenience. Probably is the case. However, it is also thought to vary between galaxies, between galaxy types, for example, in relation to their total star formation rate. And this is what we implement here. And I've just mentioned stars aging and dying. And this is going to affect the habitable zone as well, the circumstellar habitable zone, obviously. Because even main sequence stars don't actually stay at constant luminosity and temperature. On the main sequence, stars tend to get brighter as they age, which typically will move the circumstellar habitable zone outwards. The Earth, for example, is now closer or a lot closer to the inner edge of the Sun's habitable zone than it was when it formed and when the Sun was young. And stellar evolution and death, when applied to very massive stars, implies also an explosion, a final explosion that's known as a supernova, which releases more energy than the Sun will output during its entire lifetime. And this is canonically considered very bad for your health. And yeah, indeed, a planet sitting right next to a supernova will be scoured, or scorched, or even entirely destroyed. However, it's not entirely clear how deadly supernovae are at a slightly larger distance, as counterintuitive as it might sound. For example, a study from 2013 found that a supernova at the distance of 8 parsecs, that would be 26, more or less 26 light years. A parsec is around 3¼ light years. So a supernova at a distance of 8 parsecs would deplete half of the ozone layer of the Earth, therefore increasing the UV flux we receive from the Sun by a factor 2. And that would probably be bad for us and bad for animal life on the surface. But and that would probably cause a mass extinction even. But most life in the ocean, including a lot of plankton, which is shielded from UV light due to the absorption by water, would probably not be too affected by it. And so the Earth would still be habitable in the broader sense. Yes, sure. Maybe human civilization might collapse, but life on Earth wouldn't cease. On the other hand, there has to be a minimum distance at which the energy output of the supernova, if it's dumped with 100% efficiency onto a planet, makes essentially the habitable zone shift too much and out of that planet's orbit, which is why we try to compute. And following simple calculations, we put on average lethal radius at about half a parsec. But right now, I feel that even this is overestimated, a bit too optimistic. Now, at even larger scales, we need a simple way, and really simple because we don't want to get into complex galaxy evolution models. We need a simple way to model the evolution of galaxies. Now, luckily, star-forming galaxies, spiral galaxies like the Milky Way, seem to follow for most of the history of the universe a simple correlation where the rate at which they form stars, the star formation rate, is correlated with the stellar mass. And obviously, the stellar mass increasing with star formation rate with time. So this can be parameterized relatively easily and solved as a differential equation. And that results in an average star formation history. That average star formation history for star-forming galaxies speaks about 8 to 9 billion years ago for a galaxy of the mass of the Milky Way. But we also know that not all galaxies are forming stars. Elliptical galaxies are typically dead or passive. And so we need a way to introduce, a way for star formation to cease, and we call this quenching, within a short span of time. And this model therefore results in roughly 2 galaxy populations, star-forming ones and passive ones. So in the end, we have a relatively, believe me, simplistic model of galaxy evolution with time that uses empirical relations such as observe mass functions and correlations to more or less reproduce observed galaxy populations. And here, really what we wanted to reproduce was metallicity correlations. And I'm not really going to bore you anymore any longer with it. So let's go to the real meat. With all these ingredients, we can define a quantity we call galaxy habitability. Galaxy habitability here is just a fraction that relates the number of intact habitable zone planets, terrestrial planets, to the total number of stars in a galaxy. And here, let's look at its variation with galaxy mass and cosmic time. So, interestingly, and this would be the plot on the bottom right, our estimate from a completely unoptimized model falls within a factor 2 of that inferred from data collected by the Kepler satellite. So that's good. We just need to adjust one parameter to match it. Interestingly too, the galaxy habitability function has that H has a weak maximum around masses which correspond to the mass of the Milky Way. So yeah, we live in a nice neighborhood. The effects of supernovae are really negligible. We would have to significantly increase the little radius to see an effect. And that would be, for example, if we want to compute a fraction of, I don't know, intact active civilization, for example. Now, interestingly also, as a function of time, habitability seems to increase very rapidly in the early days of the universe and essentially level off between 8 to 5 billion years ago, depending on galaxy type, with passive galaxies having a higher habitability than disk galaxies. That is, it levels off even before the formation of the solar system. And this essentially means that in that model, based on this model, most habitable planets would actually be older than Earth. Earth then appearing on the tail end of the habitable planet production. Right? However, because of stellar death and stellar evolution and the way the initial mass function is structured, it also means that most of these older habitable planets would actually orbit red dwarf stars. And so small red dwarf stars, cool stars. And that potentially is a problem. It's a problem because it's not entirely, it's a question that's not entirely resolved, but as I said, the habitable zone around small dim stars is much closer to the star itself, which means that any planet in it will feel greater tidal effects from this star. And those tidal forces can actually lock them into either into a resonance, which will be fine, or in a synchronous configuration where they always keep the same side facing the star and the same side facing away from the star, like the moon does with the Earth. And this implies that there then would be a hot hemisphere and a cold hemisphere with possibly a habitable band in between. However, it also seems that if the cold side is too cold, then CO2 can precipitate and essentially it would collapse a part of the atmosphere. So the atmosphere would essentially be unstable in this configuration. Red dwarfs have also stronger stellar winds, all things considered, especially at the beginning, and the planet being closer, it would feel essentially a stronger wind. Stellar wind or solar wind is not really a big problem for the Earth, first because we have a magnetic field, and second because it's weak. But cumulatively over hundreds of millions of years, this can actually erode a planet's atmosphere if the stellar wind is strong. And this was not considered into the model. So that's a caveat. Now, so far, I've talked about, I've used a rather generous definition of habitability. Therefore, anything that's in the habitable zone and won't kill microorganisms. What about the fraction of planets which actually resemble Earth right now? Obviously, we don't know because we still have no idea how probable or improbable we are. But we can assume that some time is needed for a life-bearing planet to develop an ecosystem like Earth has. And obviously, it should be relatively protected away from supernovas, so with a slightly more restrictive criterion. Now, if we use the age of the Earth, 4.6, 4.5 billion years, as that average delay time, so few billion years to actually get a nice complex ecosystem, then we should, and that would be the plot on the right, the dashed curve, we should be slightly older than the average, but not by much. If the delay time is lower, obviously we are younger, and if the delay time is very large, then we are absolutely unique. So, some numbers. We find that between 0.5 and 1% of all stars can be expected to have a terrestrial planet within the habitable zone. And that would imply for the Milky Way about 2 billion potentially habitable planets. With the caveat that most of these planets would be a bit older than the Earth and orbit K and M dwarf stars. If we are representative, then the number of civilizations like us in the observable universe should be around 100 million. But the observable universe is really, really big. If we are unique to the Milky Way, then the delay time, characteristic time to produce something like us, must be greater than 8 billion years. Now, this is all using a simple semi-analytic model. But the core framework can actually be applied to other cases, like hydrodynamical simulations, for example. Here is a simulated image of a barred spiral galaxy that's about the same mass, somewhat similar to our Milky Way in mass and structure, but has a slightly bigger, larger central bulk. This would be the bright region at the center. The simulation, of course, has a lot lower resolution than the actual Milky Way. It's a smooth particle hydrodynamical simulation with a gravitational softening length of 300 parsec. And discounting the gas and the dark matter, it has 2.6 million stellar particles, each with an average mass of about 6 million solar masses. So, in essence, every star particle in this simulation can be considered as a big star cluster with a size of about 300 parsecs. But we know the history, age, composition of each of these particles, which means that we can actually compute habitabilities for each one. And in doing this, we find this distribution. So those two images are, or those two plots are for habitable planets and slightly restrictive Earth analogs in slices. Those are slices of about 1 kiloparsec passing through the center of the galaxy, edge on and face on. And what we see is that the habitability is lower in the bulge, in the galactic bar, and in the inner thin disk. And it increases relatively rapidly with distance from the center and has a plateau at large radii. We don't actually see a strong decrease in habitability in the outer edge due to, for example, metallicity effects. And in this context, then we would occupy a rather nice but completely unremarkable region of the galactic disk. Now, okay, that's nice. What else can we do with a bunch of stellar particles with habitability estimates? Well, we can actually look at how they network together, of course. And in particular, and really just for fun, we had a look at Panspermia. So Panspermia is essentially the exchange of biological material, be it microbial spores or just DNA, for example, across space between suitable environments with planets. And we can distinguish several types of Panspermia. The oldest scientific type of Panspermia would be radiopanspermia. Radiopanspermia is just microorganisms encased in dust grains or as dust grains, which are propelled by radiation pressure from stars. And this is actually, this arose from early studies of the interstellar medium, of interstellar dust. But it's because interstellar dust grains are elongated and they're full of organic compounds. But it's not really considered a viable mechanism anymore. The second one would be lithopanspermia, which is essentially the one you would normally think about, that is microbes encased in rocks falling onto a planet. Then we have directed panspermia, where the seeding is done through technological means, probes, for example. And finally, we can also mention necropanspermia, which is any of the above, but with inactivated biological material, so dead spores. And there have been experiments showing that microbial spores can resist the high acceleration, the high pressures, and the exposure to radiation that naked in-system interplanetary travel would entail. And in fact, we do try to avoid directed panspermia by sterilizing anything that we send into the solar system that has a chance of intersecting with the planet, so, usually. Now, moving on. More recently, we also have been visited by two comets, two icy objects with notably hyperbolic trajectories, implying that they almost certainly come from interstellar space. So transit is possible, which is why we assume that a model where debris could be possibly bearing microorganisms could be blasted off the surface of planets at planetary escape velocity by asteroid strikes. And this is described by a distribution of ejection velocities and crater radii. And these would then orbit their host star, and a small fraction of these debris can then be gravitationally boosted, for example, by a giant planet, into interstellar trajectories. So for any star particle, we can define a panspermia probability, quote unquote, because there are a lot of unknown factors based on the habitability of the target star particle and the sum of habitabilities of the possible origin star particles with their escape probabilities, the lengths of travel between the two, and a cumulative damage factor. And the damage factor is just to account that long trips in interstellar space, even shielded, will result in a large number of spores dying, possibly all of them, before reaching destination. And like I said, this has unknown factors. So this doesn't actually allow for actual estimates, just a relative comparison between star particles in the simulation, which is what you're seeing here. So this would be the panspermia probability on top, with a damage characteristic e-folding length for damage of 100 parsecs, but we also look at others. And below is essentially the inverse. That is the probability that a star particle successfully gives to other star particles, which we call the successful transplantation probability. In both cases, we compute it with different e-folding lengths, damage length. So when we do this, on average, And contrarily to habitability, we find that the likelihood of panspermia, which, remember, already includes habitability, is significantly higher in the galactic bulge than in the disk. And ignore the tick on the right because it's actually due to a satellite galaxy, not the main one in the simulation. Now, if we do a decomposition of this panspermia probability and look at all contributions, well, the total panspermia in the galactic bulge is the sum of contribution from many different star particles. That is, that the highest contributing particle is just one of many. It's a small fraction of the total. On the other hand, in the outer disk, or already where we are supposed to be, at around 8 kiloparsecs, most of the panspermia probability comes from one single star particle. And that one single star particle is often, more often than not, the target particle itself. This is because in this model, we have allowed for the possibility that the target particle and the origin particles be the same, since, again, these star particles in the simulation are more like are more like entire stellar populations than single stars. If we discard this self-panspermia, we see that really only in the galactic bulge, so the central region of the galaxy, does panspermia occur between non-identical star particles. So all in all, we see that median habitability on average increases monotonously with galactocentric radius, but it has a very small variation. It only varies by 5% on average, again, throughout the galaxy. On the other hand, panspermia is a lot likelier in the inner 4 kiloparsecs in the galactic bulge and can vary by several orders of magnitude between star particles. However, we don't expect it to be efficient except in at most 3% of all stars. But this still is with unknown factors. So, for example, we don't know the capture cross-section for panspermia. So yes, sure, an object reaches another star system. Is it going to impact a planet? Probably not. We don't know the probability of life. There are many unknown factors. And that simulation was also in a static case. That is, we didn't consider the orbits of stars around the galaxy, which actually seemed reasonable given the timescales involved. And I'm already done. So that's all. Thank you for your attention.
Thank you very much, Rafa. So yeah, there are a few questions have come through on the chat already. I'd just like to remind the audience that you can, upon when we call you up, really will unmute you. So I suggest we start with two questions we've received from Haris Katsiko-Danis through the chat. And I don't know, Rafa, if you can see these as well. But in any case,
yes, I can see the chat. Oh, yes. So how long would it take for the ozone to deplete from a close supernova?
Rafa, why don't you start with the second question?
Right. How will the habitability be affected in the case of binary, trinary star systems? That's a good question, and this is something that was not included in the model. Not much if it's a very close binary or if it's a very separated binary. Like, for example, I don't know, Alpha Centauri is a binary star, but it's essentially a trinary system with Proxima Centauri. Proxima is so far away that it doesn't matter. But yes, medium separation binaries, I would be more worried actually about the probability of forming stars and keeping them in non-disrupted orbits. We didn't include it because the habitable zone prescription depends on stellar spectrum essentially, but a single stellar spectrum. So it doesn't actually include compound emissions. That was just for convenience, for simplicity. But yeah, it's a good question, and it's definitely something that needs to be considered. Second question is how long it would take for the ozone to be depleted from a close supernova. I don't remember really from reading Gerhardt, but it should be pretty fast because the ozone would be depleted by the hard radiation coming from the supernova. So the initial pulse, not the optical infrared emission that comes later on. So it's essentially at planetary or stellar scales, it's essentially instantaneous. And how long it would take to reform this, I don't know, because I'm not an atmospheric scientist.
Thank you, Raphaël. So the first person to raise the hand with the intention to ask a question by speaking to you is Stephen Spangler. Willie, could you please unmute Stephen? And Stephen, just go ahead.
Yes. Thank you. The question I had is towards the end, you had a question about panspermia being more likely in the inner 1 to 4 kiloparsecs of a galaxy. I think that's largely on dynamic reasons, but I was under the impression that the cosmic ray intensities, cosmic ray electrons, and probably ions in the inner galaxy is also higher as well. I think that a lot of spiral galaxies show enhanced synchrotron radiation in the inner part. So was that taken into account in your models? I guess I didn't see whether that was done, or do you think that would be important?
Cosmic rays, no. We relaxed the little radius for supernovae to try and account for the fact that, yeah, if you pass, like if a chunk of rock is passing in a supernova remnant, it will actually be subject to a much higher radiation environment. But cosmic rays from in the central bunch, no, we didn't consider it. Also because the inner kiloparsec is not actually included. And the inner kiloparsec is not included because it's not, it can't really be trusted in the simulation. The simulation forms a weird, really dense clump of particles, which is not super physical. So yes, but sure. And it's true if the galaxy is in the central black hole is in an active phase, and then you have an AGN, yes, that is going to severely modify potentially habitability. Thing is, as I said, it's a simplistic model because we really don't. I mean, I don't have a good sense of how little cosmic rays or energetic particles would be to inactivated spores deep within a rock. So that will depend on the shielding, and yeah, there are so many factors we can add. It's not even funny anymore. But no, to answer your question, no, we didn't consider cosmic rays.
Okay, so we'll take another one from the chat this time, from Diederik Preussen. Diederik asks, well, says, very interesting talk, and in many of the plots, the variation of the habitability is tiny compared to its absolute value. So that leads to the question, does this mean it doesn't really depend on the galactic environment, and is it mostly set by other elements of the model?
Yes. And this is because the little radius we use for supernovae is tiny, and that's also because we assume we use a rather generous definition of habitability. So of course, a supernova at 10 parsecs would be very bad for us, and we would probably consider the surface to have become uninhabitable. But for a microorganism, it's all the same. And so because we used tiny little radii for supernovae, they don't really matter very much, except if you look at Earth analogs, so where that little radius is increased. But even then, yes, there is not much variation. It's essentially set by metallicity a little bit, because, as I said, apparently the distribution function for rocky planets doesn't really care about metallicity, and star particle age, and that's pretty much it. So yes, in a sense, it's a bit disappointing. It doesn't, where you are in the galaxy doesn't really matter very much.
Okay.
With the caveat that in the central region, the dispersion is a lot larger. So on average, it doesn't matter, but if you look at the scatter, it's a lot larger in the central region than it is in the disk. But that's just it.
So by that, Raphaël, you mean the scatter of the habitability parameter?
Yes, yeah. Exactly.
Yeah. All right, we'll take another one in person. Sylvia Wenger, ICI's very own Sylvia Wenger has raised her hand. Willy, could you please unmute Sylvia? Go ahead, Sylvia. We can't hear you at the moment. That doesn't seem to be working, unfortunately. Maybe, Sylvia, add your question to the chat. It doesn't seem to be working with the microphone, I'm sorry to say. Let's go on to Emmeline Beaumont's question in the chat in that case. Again, very interested to hear what you said, and says, I'm wondering, is it possible close by supernova went off during the past of the Earth and was close enough to impact the Earth's climate? And in another linked question, how long would the increase of temperature last that was induced by a nearby supernova?
Okay, yeah. The first question, honestly, I don't know. You would probably, I mean, yes. Like right now, we are in a slightly underdense environment, stellar-wise. We probably had a lot of close passes during the few orbits that the sun took around the galactic center. But you probably would have to ask this question to a paleontologist or a geologist. I seem to remember that there are some isotopical traces which suggest a possible supernova origin in rocks. Now, some of the mass extinctions that have occurred during the last 500 million years, those that are not super clear, I mean, that of the dinosaurs is pretty clearly due to an asteroid impact, but others might actually be due to a supernova. What the effects are is really not well. I mean, as far as I know, not many people have actually looked into the question. There have been a few studies, for example, that looked at the mechanical effects, as in the supernova itself has a lot more kinetic energy than it has radiation. And if it's at, say, 10 parsecs, then you would expect it to push the heliosphere all the way down to 1 astronomical unit. So possibly exposing the Earth to the supernova wind. But the supernova wind in that case would be like a solar wind. So mechanically, it just doesn't seem to matter very much. the temperature increase would last. So the supernova itself lasts a few weeks or a few months. The temperature increase will depend on the dynamics of the atmosphere. This requires a study with an atmospheric model, which is on the to-do list eventually. But I suppose also that if the supernova is close enough, it can actually change the chemistry of the atmosphere, and that introduces an additional complication. It's nice to play with simple models, but if you really look into it, the subject is tremendously complicated.
Yeah, so I think Tzvi Piran in his talk earlier in this series did some modeling and had some discussion of some of these aspects. So it could be interesting to go back and look at that talk too. Emmeline, I don't know if you saw it, but do check it out if you want. So Rafa, I was wondering, so as you say, you obviously had to make some simplifying assumptions, and one of them is right, the star formation history of your galaxies, which you're modeling, or the galaxy populations. And you, based on this correlation between star formation rate and stellar mass, you probably assumed pretty smooth star formation histories. We're just wondering, I mean, if you added the complication of having intermittent bursts around sort of an average evolution, would that significantly change the game? Would that reduce habitability significantly, or does that not make that much of a difference either, just because of your supernova impact radii?
Right. So that wouldn't really impact the quantity of rocky planets formed, because that depends on metallicity, which essentially depends on final galaxy mass in the model. So if you fix the mass, then you get the same answer. That would actually probably alter habitability, reduce it due to supernova, I mean, a starburst. If you have a really large amount of supernova exploding in a confined small region, that's going to probably to sterilize a volume. The volume might actually be small. Yeah, for that, we would need to go back and actually have a look at simulation. So take a cosmological simulation for any galaxy type, and depending on mass, actually go and look at simulated star formation histories, which indeed are pretty bursty. It wouldn't actually make a difference in the case of the Milky Way, because as far as I know, the star formation rate of the Milky Way is extremely boring and rather flat. Milky Way is a weird galaxy from that point of view. Had a really quiet life compared to others. So it might actually increase the habitability of the Milky Way if we took a more realistic star formation history for it, just for the Milky Way.
Okay, and sort of another follow-up question is, you had different star formation histories for quenched and star-forming galaxies, or you included the transition from active to passive and no longer star-forming galaxy. I was just wondering if you could say a few more words on why you got the result that in quenched galaxies, the habitability is higher.
Yeah, that was surprising. Part of it is due to less supernovae, and the other, but most of it is actually due to two things. Slightly higher metallicity, so you will have higher number of galaxies above the threshold, and also those are old stellar populations. Therefore, most of the stars are going to be solar mass or below. And it's essentially a bias. It's like you take a galaxy, you assume it has a given mass. In a spiral galaxy, some of that mass is going to be taken by hot hot stars, which don't live long enough and therefore are entirely unsuited. Whereas in an elliptical galaxy, all of these stars are potentially suitable for hosting a terrestrial planet within the habitable zone for long enough. And that's just it. It's because at the same mass, the elliptical galaxy has smaller mass stars. That's just it.
Thank you, Rafa. Yeah, that makes perfect sense. And yeah, I guess we've exhausted the questions, both in the chat and through raised hands. So thank you very much, Rafa. We'll close with an outlook to the next Game Changer series, which will start a month from now. So Mike Rust, who has just activated his video, will tell us a few words about that. Looking forward to the seminar series, which will start about a month from today.
Thank you very much, Mark. And first and foremost, thanks very much, Raphaël, for the most interesting talk. Habitability from cosmic to mobile scales is the motto of that series that just goes to an end. And habitability is also a term that we are carrying forward into the now fourth Game Changer seminar series, which this time will focus on Earth sciences and the habitability of our planet. The motto for this fourth seminar will be Viewing Earth from Space, the Changing Environment and Climate of Our Planet. The series will commence in early May, to be precise, on the 5th of May, with a presentation from Professor Wolfram Mauser, who just emerited from the Ludwig-Maximilians University in Munich. And he'll give a presentation on the future of food and water security on Earth. The series will be completing in the beginning of July. We don't quite know exactly if we'll manage also to have a presentation on the first Thursday in July. And of course, I'm hoping for an active participation and many colleagues who will join that fourth Game Changer seminar series. And I would kindly all ask you to pass the word. Of course, the announcements will be made through our newsletter and on the EC website. And with that, I would like to thank you all and hand back to you, Mark. Thank you.
Thank you, Mike. And yeah, I don't think there's much more that needs to be said for today, other than to thank Rafa again. A very nice excursion into the multitude of factors, and we should try at least to take into account. And I guess it sounds as if you're not quite done yet with this kind of thought experiment. So we'll keep our eyes open for more at some point. Thank you, Rafa, and goodbye.
Yeah, maybe. Thank you. Thank you, Mark. Goodbye, everyone.